Okay, I'm almost caught up on grading. And then you turned in that homework last night, but I think homework 15 will be easy to grade. It was pretty computational. So that should go pretty quickly. So I'm gonna be on top of the grading thing. Which is good because y'all have a test coming up. So I told you today that I would do one of the problems from homework 16. And so I'm gonna do that at the beginning of class so I don't forget and so we have time. And then let's see, I had some other grading papers for some of you. Shall we? Oh, and I had an extra copy of homework 16. Does anyone want to print out a copy of homework 16? Well, I got one. If anyone wants it, it's right here. Or I can recycle it, whatever. Okay. So let's see who's here. The homecoming is next week. Is that right? I try to avoid getting tested during homecoming week, but it kind of slipped my mind. Are any of you all doing homecoming stuff? Or you all are all not doing that? Okay. I mean, y'all are old, so I mean, I guess it's more of like a freshman thing that they get like, you know, I don't know. I mean, you're not old, but you know what I mean. So, okay. But yeah, when I teach like, I taught these like math for elementary education majors and they're like dead that week, you know? So, yeah, anyway. Missing today. Oh, no. It's J. All right, so let's get started then. Good morning. With, from homework 16, we're going to look at 2, 3, 10. And so it says that prove that every non-zero element of Z mod n is either a unit or a zero divisor. Okay. So here's our proof. So if we're talking about elements of Z mod n, just a reminder what that is. So Z mod n is the set of all congruence classes. Last one. Right. So this is the set of all congruence classes, right? Mod n. So I can think of these guys as that each of these is a remainder upon division by n. So this is the set of all possible remainders, right? And so the elements that end up in that equivalence class, or the in R, say, is the set of all numbers that are of the form, let's say, nk plus r, such that k is in z. So that's what we have, is the set, this congruence class is the set of all the elements that look like that for k and z, right? So that's what these congruence classes are. So I was just going to start this proof And maybe this is a little bit of overkill because we've kind of already done this, but I'm just going to start this proof by saying, like, by the division algorithm, n can be written, or any element in Z can be written of the form. A equals NK plus R for 0 less than or equal to R less than N. Okay, right. So so we have these remainders. So so then we have two cases. So and well, let's say and every congruence class of n Z mod n can be represented by some R like that, where right. So yeah. So we've kind of talked about this, but I just wanted to write that down in the front of this proof just so we can kind of be clear. Like these R's that I'm talking about are between 0 and n and so on, right? So we're talking about these congruence class representatives represented by those remainders. Okay, so we have two cases. So we have two cases for each remainder R, either the GCD of n and R equals 1, or the GCD of n and R is not equal to 1. Okay. So does that sort of make sense to you all? Because we want to say, like, we have these units and we have these zero divisors. And so we've talked before about the units. A unit is something that has a multiplicative inverse in the ring, I guess. So this is something that has a multiplicative inverse. And zero divisors are the elements that when you multiply them by another element, you get 0, right? So that's what we're looking at. And so we had noted before that elements that are relatively prime to the mod, right, are going to have these multiplicative inverses, okay? And then we also noted that elements that had something in common with the mod end up being zero divisors, okay? So we've noticed all those things from the multiplication tables. So let's just write this up formally. So we'll have case 1. So case 1 will be that the GCD of n and R equals 1. Okay, and so what does that mean? Well, by that theorem that we had, I can write this as a linear combination, right? So by the theorem, I have no idea, 1.2 maybe? I don't know, anyway. So by the theorem, there exists a U, V, and Z such that N U plus R V equals 1. So we have this linear combination. Okay, what am I trying to get with this? I'm trying to prove that this remainder R is what kind of a thing? If the GCD is 1, they have no common divisors. I'm trying to prove that it is a what? Which one? Am I going for zero divisor or unit? Going for unit is where I'm trying to go, right? So I'm going for unit. So I need to show, so if it's a unit, then I need to have that set R times something equals 1, right? So I need to show that this thing has a solution. That's where I'm trying to go, right? So I want R times something is congruent to 1 mod n. Do I have it? Well, I got a 1 and I got an R times something, so that's promising. Can I get there? Well, I can rearrange that, can't I? Yeah. So I'm going to rearrange that. And so I get thus, I get RV minus 1 is equal to n times negative u, if I rearrange that thing. And that implies that RV is congruent to 1 mod n by definition. Is that clear? Does that make sense? So we got that GCD bit. That gives us the linear combination. We can rearrange and use the definition of mod to get that that's congruent to 1. And then that means that R, well, I guess we get RV is equal to 1, which implies that RV equals 1. And that implies that V is the solution to the equation Rx equal 1. And that means that R is a unit. Okay. Yeah, sorry, I keep using this implies arrow instead of words, but anyway, or is that okay? Yeah. Okay. So case 2. So yeah, so in case 1, I had that if the GCD was 1, I end up getting that R is a unit. And now what am I going to get? If the GCD is not 1, what am I going to try to say? It's going to be a 0 divisor, right? That's what we're going to have. Okay, so case 2. Okay, let me see if I can. May need to get this so that we can see. Is that better? Okay. So case 2, we're going to have that the GCD of N and R is equal to D, which is greater than 1. Okay. So by that theorem, whatever that theorem was, there exists a U, V, and Z such that N U plus R V equals D. What do I want to get? I want to get that R is a 0 divisor, right? So I'm trying to get that R times something is some multiple of N, right? That's what I'm trying to get, that R times something. So I want that R times something is equal to 0, right? So I need to get that R times something as some multiple of N, right? And I don't quite have it yet because what I have is that I have an R times something and I have, this is a multiple of N, but that's not a multiple of N, right? But what do I know? I know that D divides N. Why? Because it's the GCD, it's the greatest common divisor. So since D divides N, what does that mean? I have some K, right? So since D divides N, there exists some K in Z such that N is equal to DK. Okay. So I'm getting there. So what I want to do is I want to multiply this through by K so that this part turns into a multiple of N. Okay, so that's what we're going to do. We're going to multiply this through by K. So thus we have, by multiplying both sides by K, we have that NUK plus RVK equals DK. Well, what's DK? DK is N, which implies that NUK, well, I'll put it below. So we have NUK plus RVK equals N. So then I can subtract that over and I get RVK equals N minus NUK, and then I can factor out the N. RVK equals N times 1 minus UK. And what does that give me? Well, that gives me that R times something is a multiple of N, right? So let me go over here and finish this out. We're almost done. There's an eraser. Okay, so that gives me that R times VK is equal to N times 1 minus UK. So that's by theorem, was it 2.3? I don't remember. So there's a theorem that allows us to go back and forth between the mod stuff and the congruence class stuff. Okay, actually, maybe let's say it this way. So, but from there I can say thus, by definition, we have RVK is congruent to N times 1 minus UK mod N, right? So then I get that, and maybe you could reduce it here. You could say that's congruent to 0 and be done. But I guess I'm doing it this way. I don't know. So anyway, you can kind of reason with it in the mod stuff, or you can reason with it in the congruence class stuff. So it's kind of either way, whatever makes sense to you. So this gives me that R times VK is equal to 0. Actually, let me do it. Yeah, I don't know. Times 1 minus VK, which is equal to 0. Which implies that R is a 0 divisor. So is that clear what we did there? Okay, so those are the kinds of strategies that we're using over and over again, right? We, when we're trying to show that something is a unit or a 0 divisor, we have this GCD thing, we've got this linear combination bit that we use over and over. We rearrange things. We can go back and forth between writing it in mod versus writing it in these equivalence classes notation. So we can kind of go back and forth between that. If we want to prove that something, oh, well, okay. I've been grading homework 11, like slogging through homework 11. And I think the hardest thing in homework 11 is you're trying to, in so many of them, you're trying to show this if and only if P is prime, right? So how do we show something is prime? Well, we have two methods, right? One is to use the definition. So to use the definition, I want to assume I have a divisor of P. And once I assume I have that divisor, I have to show what? That divisor has to be 1 or P, plus or minus 1 or plus or minus P, right? So I've got to start with assuming I have a divisor of P, and then use my assumptions to show that that divisor has to be plus or minus 1 or plus or minus P. The other way we can prove something is prime is by using theorem 1.5. Right? So theorem 1.5 says, what does it say? I have no idea, but I remember that that's the one that we used. Okay, so theorem 1.5 says, okay, P is prime if and only if it has that property whenever P divides BC, P divides B, or P divides C, right? So that's the other thing we can do to show something is prime. So we can show, okay, let's assume that P divides BC, and then show that using my assumption that it must be the case that P divides B or P divides C. And if I can get that, then that's enough to say P has to be prime. Okay, so those are just some of the strategies that we're using over and over in this section of material. Yes.
On the board, right above case 1, when you listen to, what's the last one?
This, so the GCD of N and R is not 1. Other questions on this? I kind of went through it fast, so sorry, but we've been proving things, and homework 16 is like all this over and over, right? You're using the definition of unit, the definition of 0 divisor, and you just do this kind of stuff over and over. So, so that's homework 16. Okay, any other questions on homework 16? Were there other ones that you had needed a hint on or were stuck on or anything? I do have some office hours tomorrow, and I will be there in person, y'all. It's going to be amazing. Okay. So, or if you need to meet with me at other times tomorrow, I'm relatively free in the morning tomorrow. So if you needed to meet with me in the morning, you can't come to the 2 o'clock office hours, that's fine. You can meet me in the morning. Or if you just have questions over email, like, hey, I need a hint on this, or hey, I tried this and got stuck, just let me know. Okay. All right. Okay, so for today, I have this worksheet handout thing. And so I'll hand it out to you online people, Brandon and Benjamin. This is posted on Canvas. It's called Section 3.1 Handout. So if you go to Canvas, it's there. Okay. So, yeah, so the first page is really talking about equation solving in different sets with different operations. Okay, so I'm just going to give you a little bit of time to think about that in your groups and work together on finding solutions to some of those that you can solve. And yeah, that's what we'll start with. So for those of you that are online, if you don't have that paper, I'll go ahead and write down the first questions on the board so you can see them. Come in, Brian. Come in. I guess here, if I want to be pedantic here, I can write x squared minus 7 x plus 12. Now you might need to use your classmates on the solutions in ZMAT 12 because you're going to check them all.
It should go there because it's the same thing you said.
What are we getting in ZMAT 12? 3 and 4, obviously. I don't know where. What else? 0 and 7. Any others that work in there? Did you check them all? Yeah, and so what are we seeing? Well, in the real numbers, what are our solutions? Just 3 and 4. why does this work in the real numbers? So we can factor this, right? So we get x minus 3, x minus 4 equals 0. And so then we get x equal 3 and x equal 4. So how can I go from here to here in the real numbers? Yeah, because I have no zero divisors, right? So going from here to here is that's because there are no zero divisors. In the real numbers, right? There are no zero divisors in the real numbers. So I can jump straight from here to here. I can say, the only way this is gonna work is if x minus 3 is equal to 0 or x minus 4 is equal to 0. That's our only option because there's no way I can multiply two non-zero things and get 0 in the real numbers. Okay, there are no zero divisors in that ring. Okay, and what about here? Well, we get the same solutions we got in R show up here too, right? So we also have 3 and 4. Right, but in this ring, we have some zero divisors. So we know that if we factor this, we'll get x minus 3, x minus 4, right? So what we can get is like, if this times that equals 0, right? So we know that if this is equal to 0, I have negative 3 times negative 4, which gives me positive 12, which is 0 in Z-mod 12, right? So we get x equal 3, x equal 4, x equals 0. And then the other one was what, 7? Yeah. So if I plug in x equals 7, I get this is 4, and that's going to give me 3. And so 4 times 3 is 12. Yeah, William?
You also, since ring mod 12, that converts out to 12 is 0. And you get to factor out an x.
Where? Here?
Yeah, or like in the original equation. You wrote it with congruence classes.
Here?
Yeah, the 12 is a 0. Right? Congruence classes.
Yes, right, true. Yeah, so we could have written it that way. So this is the same thing as x squared minus 7 x equals 0. And so here, yeah, you can factor out an x, right? And then we get x minus 7, right? So that gives you the 7 and the 0 there too. Yeah, nice. That's a good observation. Yeah,
So-
Sophie?
Sorry. So we did that as well, and then how would you get the 3 and the 4?
So the 3 and the 4 are from this way of thinking about it.
But so you would have to do both ways. You could.
Yeah, and that's where it gets a little tricky when you have zero divisors. I mean, I kind of think like, even if I did this and that, I would still not feel confident I got them all, and I would check every element of Z-mod 12, right? So that's how I would do that, because you could have missed one or something, I don't know. But yeah, so both of these ways kind of give you how to see it, in the way we're used to. So that was good. Yeah, thanks.
So like, if you can prove there's only like so many factorizations of a polynomial, does that mean that that's how many solutions you have? Like,
That's a really good question. I don't know. I don't know the answer to that.
I guess, can we use the quadratic formula in like mod 12?
I would not use the quadratic formula in mod 12 because we have zero divisors, right? So since it's a finite ring, you can just test them all, so yeah, I mean, I'm not trying to say that you're not onto something, because maybe you are, like maybe there's a way to prove it that way, but since it's finite, I say just try them all, just to be sure. But yeah, I mean, you can't use the quadratic formula in the same way you can in R because of the zero divisors. So and we noted before, like here, since the spacing between that 3 and 4 is 1 unit apart, then you would need zero divisors that are 1 apart from one another. So in other words, like the zero divisor is 6 times 2, like 6 and 2 are zero divisors, right? Because 6 times 2 is 12. But like those don't show up in this because these numbers are 1 apart. So we're looking for zero divisors that are 1 apart. So 3 and 4 are the ones that show up. So are there others that are 1 apart, like 9 and 8? are both zero divisors, but like they don't show up here, do they? Well, anyway, so well, let's see. Yeah, I'm actually not sure. I'm just kind of spouting these off. But anyway, what I'm saying is that there are other pairs that make zero besides just 3 and 4. So you kind of need to consider those things. But so there may be a way to like systematically like look at the structure of this polynomial and like prove that there aren't any other ones. But like, I don't know that that would be less work than just testing all the things. So I don't know. But it might be an interesting question, like what polynomials. So like, are any of you OSU teach folks? Any of you doing? Yeah, okay. So like you'll take a class where you do research, like a research methods class, and you actually do like a research project in math. Like that could be maybe an interesting question for a research project, right? So like what kind of polynomials, and like think about the mod, think about what the zero divisors are, and can we say something about factoring these polynomials to make sure we get them all? Like that's a really good question. So yeah, someone may have done that somewhere, I don't know. Okay, so look at the next question. Did anyone make any progress on this one? Well, what question do we need to ask to be able to tell if we can factor this thing? Yeah, Colin?
So I wasn't really sure. I was having trouble just thinking in my head what happens when we're doing a polynomial instead of just strictly a real variable. So I just manually did the completing the square. And it still seems like if you do it that way, it guarantees that it has to be 3 or 4, which I mean, those are technically polynomials, they're degree 0 polynomials, so that works, but I don't know.
Yeah, so I mean, the question is, were all of the algebraic steps that you did legal in this new set and these new operations, right? I mean, okay, so polynomial addition and polynomial multiplication are pretty similar to addition and multiplication in the real numbers, right? I mean, you kind of just add them together, right? Add up all the parts. So, so the question is, are there zero divisors in polynomial rings? Can I have a polynomial multiplied by another polynomial equaling 0?
When one of them is not 0.
When one of them's not 0? They're polynomials, not any other kind of function. Yeah, so if I had like some p of x multiplied by some q of x equal to 0, does that mean either of those have to be 0, or is it possible? Yeah.
Well, so they're both polynomials, they have some number of roots.
Mhm.
And if you want that equation to be 0 everywhere, that means you've multiplied 2 polynomials and you've wound up with a polynomial where every real number is a root. So those 2 polynomials had to have infinitely many roots to begin with, right?
I didn't follow. Say it again.
So you just have like P is some polynomial, it might, whatever degree it is, it has maybe that many roots or less with multiplicity. And then Q has some number of roots.
Okay.
So they have some number of zeros. And what you wound
Maybe.
up,
Yeah, maybe they have some number of zeros. Real zero.
with, yeah, reals or, okay, so.
Yeah, so what you're invoking there is the fundamental theorem of algebra, right? Which that's like the pinnacle of this course. Actually, I don't know that we're gonna get there. I think it's right, it's at the end of chapter 4. It's like chapter 4, section, yeah, it's like, yeah, so it's theorem, okay, so it's in section 4.6.
Are we allowed to in this question, is X allowed to be complex? It just says the polynomial has a real coefficient.
Yeah, so the coefficients have to be real, right? So it could have complex roots,
So,
but I mean, according to the fundamental theory of algebra, which we haven't done yet, but.
so P and Q have some degree and they have only that many zeros or maybe less. But if you multiply them and you wound up with a polynomial that has every single real number in the root, because it's always zero. So I want to say that those other two polynomials had to have every.
So then it would have to be a power series. If it has infinitely many roots, it would have to have infinite power,
Well,
you know,
so
William?
I think what he's saying is like in the coordinate plane, like the two polynomials have a function, like, or we can visualize them. So when you multiply them together, you just get y equals 0, which crosses 0 infinitely many times.
Oh.
if there was any complex number for either of those polynomials, if there was any complex number where both of them didn't give 0 as an output, then that would be a number we could put into the product of those polynomials and it would still output some non-zero.
Non-zero thing.
So to satisfy that equation for any value of x, it means that at every single value in the complex plane, one of them is 0. So
Okay, so what I think you're drawing on, if I understand your argument correctly, is you're thinking about this like x input by x input, right? So if we had like, okay, so if I had some x value, I would have a value for p and a value for q, right? At that x input, agreed? And so what I'm saying is that, or what this is saying is that in order for these two to equal that constant function, I would need to have that p at that, I'll just call it a, p of a times q of a has to equal 0 for every x element a. Oh shoot, I forgot to. What? Oh, hey, I'm teaching class right now. Can I call you back in a bit? Oh, did you have an emergency or?
I don't know.
Oh, well then don't come. Do you want me to call you back in a minute to talk about it, or is that answer your question? Okay, feel better. Okay, so then it breaks down to do the real numbers have 0 divisors, right? Because if these two values multiplied together equals 0, you know, are those two values non-zero? So you're kind of taking so does that like capture your reasoning maybe? Or maybe that's a different argument.
yeah, I think mine depends on the complex numbers not having 0. Wait. Yeah, the complex numbers that have no 0, which I think they don't.
Yeah, I think they end up not, yeah. So we'll get there. Okay, so sorry if that was too much, but we can also think about these guys. We have a way of writing down polynomials, don't we? Right? We have a way of writing them down. So we know that p of x is equal to a n x to the n plus dot 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 plus a1x plus a naught, right? So that's one. And then q of x I can write down as b k x to the k plus dot 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 plus b1 k x plus b naught, right? So I can write that all down, okay? And so I can multiply that all out, and I'm gonna get some big old polynomial that's equal to like a n b k x to the n plus k, and then all this stuff, and then it goes all the way down to a naught b naught. So I'm gonna get this whole big thing. And if that equals 0, then that means each of these guys, each of those coefficients has to equal 0, right? And so then I get to the real numbers having no 0 divisors. Okay, so since there are no zeros in the real numbers, then these guys all have to be, it either has to be, oh shoot, could I have like Okay, if this guy equals 0, then either AN or BN is 0, right? So maybe I have to deal with that a little bit more because like what if AN is 0? Oh, it can't be 0 because it's the leading coefficient. Anyway, so you can like work it down and get to where using the fact that the real numbers have no 0 divisors, that the polynomials have no 0 divisors. So you can kind of see the argument there a little bit. Yeah. I didn't mean to belabor this point. But the polynomials have no 0 divisors. Let's just say that.
So you mentioned the thing, as long as at least one of those polynomials is 0 at any point, you could do this. But then you mentioned power series.
Well, because I didn't understand your argument. I thought you were saying that these guys had to have infinite powers or something like that. But William cleared that up for me. So I wasn't understanding what you were saying.
Yeah, I guess sort of that is what I meant. I meant that they have to have an infinite number of roots, and those roots need to be every single real number. Or
The product of those two things, yeah.
right, or so between those two polynomials, at least every single real number is a root of one of them. And I don't know, I think that means you have to have them being 0 everywhere, otherwise they'd be, I feel like one of them would be discontinuous if it didn't. But
Yeah, because these guys are forced to be polynomials,
Yeah.
which are continuous everywhere. Which, do we know that in this class? I don't know. So it's like, so anyway, okay. So since we get that the polynomials have no 0 divisors, right? Then we can factor this out and solve it. And we'll end up getting the same answer as we got in the reals. We're gonna get just 3 and 4, right? And we'll have to think about the 3 and 4 as a constant, as a polynomial, right? A constant function, okay? Because the things that we're dealing with here in the set of polynomials are all polynomials, they're all functions. Okay. All right, so what about this one? How many 2x2 matrices with real entries satisfy that equation? So we have to think about, like, do these 2x2 matrices have 0 divisors? Okay, is it possible to multiply 2 matrices and get 0 where the matrices are non-zero? So do you remember matrix multiplication? We can play around with that a little bit and see what we can get. Okay, so if I had like A, B, C, D times E, F, G, H equals 0, what would that mean? That would mean A, E, B, G, A, E plus B, G. I multiply it, that's the top one. And then I have A, F plus B, H. And then I'm gonna let y'all fill in the rest, so you have to think about it. So we can kind of like fiddle around with examples and see, like, can I make this happen? Like, what if I had like 1, 0, 0, 0 multiplied by like, I mean, if they're mostly 0, like, can this work? What if I had like 0, 1, 0, 0, or maybe the ones like down here, right? Will that end up giving me 0? So I get 0, 0, 0, 0. Yeah, I think I can, right? I mean, does this give me 0? So I get 0, 0. Do I ever multiply that by that? Yeah. 0, 0, 0. I think this gives me 0, 0, 0, 0, doesn't it? I'm pretty sure it does. I don't think I ever end up multiplying that one by that one. So I do that, and then I do that times that. So this one actually shows that it's not, that it does have zero divisors, because I have these two non-zero matrices multiplied together, but they're equal to zero. So I just kind of was fiddling with where to put ones to make this work. But yeah, I mean, sometimes you just have to kind of play around and see, like, at first I put the one up here, and then I was like, I'm like, oh, whoops, I'm gonna get a 1 times 1. So I'm gonna get a 1 in there. So then I was like, well, maybe I'll move it down here and see how that goes, So we just kind of play around a little bit and try to see if you can make a zero divisor. And so we did. We made a couple of zero divisors here. So those, so that tells me that in this ring of matrices, I have zero divisors. So I can't just do algebraic operations like I do in R here. I have to be a little bit careful, because I can't just solve those equations. So I'm going to skip 4 because I don't want to get into a big long thing, but let's look at number 5 and see, like, I have the definition of a ring down here at the bottom of the paper. And then also we have a commutative ring, ring with identity, integral domain, and field. And so those definitions are scattered throughout this worksheet. But I want you to think about these numbers. We have the real numbers, the integers, the rational numbers, which we talked about those 3 in class on Monday a little bit. Let's think about in your groups, the odd integers, the even integers, Z mod n, polynomials with real coefficients, and 2 by 2 matrices. And think about, like, what of these properties do they have? Or I think actually it helps to think about what ones do they not have, because they have a lot of the properties. Like addition is usually good in most of these, right? But you want to start to think about, like, what are these properties do they have and not have? And like, we're just going to spend the rest of class. Oh gosh, we only have 5 minutes. Okay. So I want you to actually, I'm going to have you focus in on the odd and even integers. Okay. So focus in on the odd and even integers for the rest of class today. And just talk in your groups about what properties, what of these ring properties do you think they have and don't have? And we'll see what we can come up with. We're not going to finish that today, but. Hey, Brandon, I didn't see your homework 15. Did you need an extension or anything? Anyway, you can email me about that, okay?
Okay, I will.
Oh, what'd you say?
I will. I'll email it.
Okay,
you about
thanks.
it.
Yeah, just email me and let me know what's going on.
Yeah.
Oh, do you want to do a little quiz on Friday? For a couple of minutes? You're like, do we want to? No. Okay, fine. Just trying to be helpful.
Distributed but not closed. Or does it have to be close to be?
That's a good question.
It's like, no, because for closed, there's like, it has to be in the thing.
It has to show up in there.
For
Could
distributed-
you take elements and put them in the distributed property rules and get outside of it? So maybe, yeah. So I hadn't thought about that before, because to me, I'm like, okay, it's not close, so it's not a ring, so who cares? You know?
Yeah, that's true.
But that's a good question. Like,
Because I think the odd numbers would still be distributed, but they're not closed by their multiplication.
right. Well, because we're borrowing the same properties from the integers, right? And since the integers have distributive property,
So
yeah. So then it's like, if you take numbers and you end up outside of the ring, then what do you say? It's like, I'm not sure, but yeah, you should get distributed for free because it's a subset of the integers, right? So, yeah.
When it says which algebraic rules, are we taking algebraic rules from like the list of stuff we did?
That's what we're going for, yeah.
Okay.
Yeah. Yeah, and maybe we should have said that, like, what ring properties or what, are, because that's what I'm kind of looking at, like, you want to look for like closure and associative, commutative, additive. Yeah, I mean, most of these, like, you're gonna probably get associative for most, like, Yeah. Okay, what did you see for the odd and even integers? What did you notice about odd? I kind of heard a bunch of people saying
The only one we found that didn't work was the closure or addition for odd.
odd is not closed under addition. Is odd closed under multiplication?
No. Three times 3 is 6.
It's nine.
It's 9.
You're right.
Oh, yeah. I think we showed it. I know. It's like, this is why I don't add numbers in front of people. They're like, don't you have a PhD? Like, shut up.
Well,
Yeah.
odd
I know, right?
means you don't have a multiple of 2, so for like one of the primes isn't 2, so if you multiply them together, you don't introduce any new primes, so they can't be even.
Yeah, and we proved this in general, haven't we? Like an odd times an odd is an odd. Like we proved that, like, I don't know, back when we first started thinking about definitions of odd and even, right? Yeah, so we've seen that. So it is a closure or multiplication, but not closure for addition. Yeah. And so then Felicia's question was interesting because she was like, does it have distributive laws if it's not closed? Which I hadn't really thought about, but I think you get that for free since it's a subset of the integers. So we're going to talk too before too long about a subring of a ring. If you have a ring and then you have a subset of that ring, is that subset in it of itself a ring, right? And what do you have to check? Well, you're going to get some of those properties for free just because it's a subset of that ring, right? So you're going to get some of the properties for free. You just need to check things like closure and some other things. So if you know that something is a subset, okay, I'll let you go. If you know something's a subset of a ring, then you don't have as many things to check. Some of those come for free. That's the point. Okay, we'll see you Friday. No quiz.
Question on